Okay, we're going to look at probability distributions. And to do this, we're going to begin by making some definitions. And so the first definition we want to work on is a probability experiment. We're going to build up the resources we're going to use. So these definitions are, I want to say, minimalistic, but and a probability experiment, in quoting the book, is an action or trial through which specific results, counts, measurements, or responses are obtained. So an action or trial, through which specific results are obtained. Using the book definition. And then we have an outcome. And an outcome is the result of the trial. So it's the result of one part of the trial. And you'll see what the individual means. So this is the result of a trial in a probability experiment. And this is a singular. Now, if we take all the outcomes that can happen, all possibilities, that gets called a sample space. And sample space is the thing we'll be working with a lot. And that is all possible results, outcomes of a trial. And so we have sample spaces which have everything that could happen. And I guess if we extend the definition, we could say all results, outcomes of a trial or a probability experiment. And then we have an event, which is one or more outcomes. And so we have an event, which is one or more outcomes of a probability experiment. And so what we're looking at here is a way of talking about what can happen, all the possibilities, what does happen, and kind of what different combinations could happen. Let's try to work on showing an example of this. I'm going to try to follow the book's example. I do like these examples. Plus, it gives something you can reference back in the book. So, if we ask people their blood types, what ends up happening is that there are 4 major blood groups: O, A, B, and AB. Those are the blood groups. And so this is a sample space. If I randomly grab people and test their blood, I am going to get one of these. Nothing else. This is all the possible outcomes I could get from my trial or experiment, which is randomly grabbing someone and testing their blood. And then we also have Rh positive and Rh negative for each one of these groups. And so if we look at the full sample space of the blood types, and if they're Rh positive or Rh negative, I could go, well, O, and then I get O positive and O negative, A positive and A negative, B positive and B negative, and AB AB positive, and AB negative. And this, in its entirety here, is my sample space of a probability experiment where if I were to take people and I were to test their blood, these are the only outcomes I could see. And that is listing the sample space of a probability experiment. And what we can see there is that really quickly, a few options give us a lot of possibilities. Well, we can talk about events in some different ways. So I can talk about a simple event. Right? So we have our probability space. We have our possible outcomes, and we can talk of a probability as a simple event of being an event that consists of one outcome. And so this is an event that consists of one outcome. And so using the language that we have here, I can toss a coin and roll a die. So if I toss a coin, these should be random things. Notice I'm trying to get randomness to come into this a little bit more here. I'm picking people randomly, there's a randomness, but there's some underlying mechanism. Tossing a coin and rolling a die, kind of, they're the ways we do random. Okay, tossing a coin, I can get heads or tails, and rolling a die, I can get 1, 2, 3, 4, 5, or 6. And so this is the probability space for this. This is the probability space for this. But if I do them together, if I toss a coin and then roll a die, well, I get a tree of these two. I'm going to put it down here in this space here. I tossed a head, rolled a 1. Tossed a head, rolled a 2. Tossed a head, rolled a 3. And so on. In fact, I get 12 outcomes in this particular probability space. And a simple event has only one outcome. And so if I toss tails and rolled a 1, that is a simple event. Because there's only one outcome in the list of all these outcomes. Even though I combine two things together, the probability space has these simplified outcomes. If I do these two events, I'm going to get one of these. And so a simple event is one outcome only. Where a non-simple event has multiple outcomes. And so a non-simple event would be, let's say, toss heads and roll an even number. And so I'll change colors for that. If I toss heads, I'm going to be here, and the even numbers are these. So this particular event, tossing heads and rolling an even number, there are 3 outcomes that satisfy that event. And that's not a simple event. And so we're able to talk about our events, or the type of events we have, in how the outcomes relate to our probability space. Now, what really drives how we figure out what's going on? If you noticed, I had 2 things linked together, and I said, oh, there's going to be 12 things here. And one of the things that's going to drive probabilities is how we count. And so we have the fundamental counting principle, which we're going to build upon. And it says if we combine events. So if we're going to combine events, that we're going to have multiple events, if one event occurs, whoops, get my R in there, occurs m possible ways, and another event occurs n possible ways, combining these events occurs m times n possible ways. So if we go back to my tossing a coin and rolling a die, there were, we'll let m of the coin be 2. I'm just going to keep using the variable m, as you'll see for my next example. And m for the number of ways for the die as 6. Well, the total possible outcomes were mc times md, or 2 times 6, which equals 12. Now if we come back up here, where's my scroll bar? There we go. I did end up with 12 outcomes. And so the number of outcomes is multiplying. One of the things you're going to find is it doesn't take long for the number of possibilities to multiply to very large numbers. And I'm going to extend this a little bit to work for multiple things. And then we'll look at a couple of different examples. So the fundamental counting principle, well, I actually don't look at it as two things, I look at it as multiple things. If you can choose multiple options or probability spaces, they combine by multiplication. Now we're going to expand and hone this rule over and over, and that just says if I have event 1 and event 2, or not event, if I have, and I combine all these simple events into one combined event, they multiply. Let's look at an example of this. We'll look at two examples of this that are actually fairly useful. And I'm going to go to a wedding. And they have a menu. And usually you go to an event and they'll have a menu where they'll choose 2 meat dishes and so many. So we'll just say, let's say we're catering an event. And we give the option of beef, chicken, fish for the meat. And then for the vegetable, let's see, corn, green beans, and what's my favorite, Brussels sprouts. And for the starch, rice or mashed potatoes. And then for dessert, I'll keep it simple, I won't go into too detailed. Pie, cake, or pastry. Now, and you usually get a little card and you check off, I want chicken, I want Brussels sprouts, I want rice, and I want to have a pastry as my dessert. And they can slap this together coming through. But these options actually create a large possibility. If I were to eat this every day, but to choose something different, well, I could have 3 options of meat dish, 3 options of vegetables, 2 of the starch, and 3 of the dessert. So 3 times 3 is 9. 18. Let's see, 4, carry my 2. There's 54 different meals I could eat with different combinations. And this is the key to like options in buying or in our the way we design kind of factory outputs where everyone can get their own personalized experience, but you can do it from simple options and they add up really quick. It also has the opposite side. There's been a lot of literature written about the psychology of choice overload. Very example, different cultures have different market choice. The example in the book called The Art of Choosing talks about they were interviewing Russian people, and they used an example for the marketing of soda. And they said, do you want Pepsi or Coke or root beer? And they're just like, I want a soda. And in Russia, there's only a few options for soda, where in the U.S. we have major brand recognition and a lot of different choices in soda, which means that we are very specific about choosing which soda we get, where in the Soviet Union they will want a soda only. And they're happy to get anything that's bubbly and sugary because they have limited choice in sodas, or at least used to. I mean, this research was done in the late 90s, early 2000s. Now, the opposite can happen when you have too much choice. You can actually be paralyzed to make a decision. I have going to buy a salad, frozen, trying to choose which salad dressing to get because there's like 20,000 different salad dressings. And what we'll find is once you start increasing the options here, let's say I have, let's say I was actually planning to make a meal, but I didn't know, whoops, I didn't mean to do that. Let's see if I can get back here. There we go. Recenter everything. If I were planning to make a meal, but I didn't have any idea, didn't have a recipe, didn't have anything I was going with, and so I go to choose my meat. Well, now I have, just thinking about Price Chopper's aisles and going through, probably have about, at least 50 clear options of cuts of meat to get. Probably closer to 100 or so. And then I go choose the vegetable, between the frozen and fresh vegetables, there's a good 400 and some options here. And then I go through starches, and I'll say there's about 20. And then dessert, in American culture we love our dessert. I'd probably wager that there are a good 1,000 dessert options. Just by choosing ingredients, like just pick a cut of meat, pick a vegetable, pick some starch, and then pick something from the dessert aisle. Now I have to choose a meal that works with it. And in my mind, I'm trying to figure, well, that cut of steak would go very well with, green beans and rice. And then I'm going to top that all off with a Sara Lee cheesecake or something. And this is an effect that we have, and it's choice option. We as human beings, we like to calculate risks and advantages. And to do that, we try to figure out all possibilities. There's a point to this. And sometimes in things, and shopping is an example of it, we can get overwhelmed with the amount of choice we have. It's sometimes a lot easier to choose from limited options and still create something functional. One of the advices for people to have is to have recipes and to add to your recipe book, not choose. Or sometimes it's fun to randomly just pick something else. Notice how I'm dancing about how probability comes into some daily life functions here. And what we're going to do is we're going to calculate risks and advantages. That's what the statistics help us do, is put measures to decisions. But we have to realize putting together a small set of choices very quickly adds up the possibilities. And so we'll be dealing with some big numbers as we work on this, and we'll have the tools to work with big numbers. All right, another way the counting principle rears its head. Sometimes we could think of in passcodes. And so if I have a 4-digit pin, and I can go 0 through 9 on each of them, I have 10 options. 10 options. And so I have 10 to the 4th possible pins. Now what's really neat about that is if 0, 0, 0, 0 is an option, then a 9, 9, 9, 9 is an option. Which means I have this, one more than this. Well, one more than this is 10,000, or 10 to the 4th. Because 10 times 10 times 10 times 10 is 10 to the 4th. And this is used in security or picking codes a lot. So sometimes if like you can't repeat digits, so if I can't repeat a digit, then for my first choice, I have 10. Then for my second choice, I have 9. Now I have 2 digits I can't repeat. I only have 8. And for the third choice, I only have 7. And so if I can't repeat a digit in a pin, if I multiply these together, what do I get? Do not have my calculator handy, so that's 56 times 9 is 4, carry my 5, 504 times 10, 5,040. And so we're just a little over half of the options we had by doing that. But I could say, you know what? I could pick any number plus any letter of the alphabet. And now I have the 26 letters of the alphabet. I have 36 times 36 times 36 times 36. And I know calculator will be, that's a bigger number. And so this counting principle shows us that as we increase our options, our numbers get high. I actually had a calculator sitting here. I just do not know where I set it. It's probably under this, under this pile of books. I mean, if you ever come to my office on the mount, you'll see the pile of books is me to a T. So let me go 36 times 36 times 36 times 36, or 36 to the 4th power. If we use our notation properly, that's 1,679,616 options. So going from 10,000 options if we just use numbers to over 1 million options if we add letters in for a 4-digit pin. And I hope we can appreciate this is something that will get discussed a lot with electronic security. How do you guess things or coming across? Well, the more options you have, the harder it is to outright guess. All right, I want to pause this video here. We've started to introduce what we're looking at, which is probability spaces. And we've shown that there are events that come into it. And I'm showing that as we add events together, or they multiply, and this multiplication means our probability spaces are going to get very large numbered fairly quickly. And we'll look at now how we can measure probability spaces and try to get some predictability from them, and keep throwing some examples, because it's not just dice and cards, but we'll probably go to things like dice and cards a lot because they're easy to visualize.